All right, in question 3 of online lesson 3, labor demand, we're going to look at the optimal amount of labor a firm demands and what happens to it if the firm all of a sudden expects to be able to sell more product in the future. And this is isolating the output effect. So we're not going to have a substitution effect here. We're just going to have an output effect. Okay. Again, capital, physical capital is K. Labor, quantity of labor demanded is L. We have technology in this particular model, and we're going to hold it constant at 8. And the firm is producing 936 units of its product currently over the long run, right? So that's this long run project 936. And it uses this technology, this production function, this long run production function to determine its optimal capital labor mix or its optimal capital labor ratio. Okay. Now, suppose a firm pays workers $18.60 per hour. So W is $18.60. I'm going to start recording these values right here. So output is going to be equal to 936. Technology is equal to 8. The wage that is paid to the workers is $18.60 an hour. The cost of capital is equal to $9.30 per hour. And maybe its costs are currently $5,998.5. So $5,998.50, right? Solving the following equation for K yields one of many isocost lines. And in the graph below, we have 1, 2, 3, 4, 5 isocost lines graphed, right? We're gonna come up with an equation for one of them, right? Now, cost at time I is 5,998.5, right? And the wage is $18.60 per hour, and the cost of capital is $9.30 per hour. Okay. Then we want to solve for K. So to solve for K, let me do it down here in Desmos. What I'll do is I'll do it right here. Let me widen this out. Okay, so the cost is equal to W times L plus, I'll do 18.60 times L plus 930 times K, right? Well, the first thing I want to do is I want to subtract this from both sides of the equation, right? Actually, what I'm going to do is I'm going to flip this around. I'm going to move the right side to the left side. And then I'm going to subtract, I'm going to copy all this. I'm going to subtract this from both sides of the equation, right? Okay. And now I got to divide. I got to divide this by the price of capital. And I got to divide this by the price of capital, right? And so this ratio here is that number. And this ratio here is that number. So let's go ahead and do that. So the first ratio is 645. And the second ratio, the ratio of the prices per hour, is 2. Okay. Then I'll clear this out. All right. And that's a graph of one of these, right? It's a graph of one of these lines. Okay. Using the assumed values above, solve the long-run production function for blank to derive the what in the graph? Well, we've already derived an equation for the ISO cost lines. The only other thing that's in this graph the only other thing in this picture that is graphed are these curves, right? And those curves are isoquants. Along one of these curves, the quantity the firm can produce remains constant as the capital labor ratio changes, right? And we're going to do one of them, right? We're going to solve the production function up here. Whoops. We're going to solve this production function for one such one, right? We're going to solve it for the we're going to solve this production function for the ISO quant that corresponds to 936 units of product, right? We're going to solve it for K. Now, though there are only 5 of these ISO quants in the graph, in theory, there are infinite many, right? So the first thing we did is we got rid of the square root. To get rid of the square root, you square both sides. You square the right side and you square the left side. And that's what we have here. We have Q squared. And then that is equal to T times K times L. And then I'm going to take the right side and put it on the left side. And then I'm going to divide both sides by T and L, right? So we end up with Q squared divided by T, and then in the denominator, we're multiplying T by L, right? So we need to find out what the coefficient of 1 over L is, right? So we have to square Q squared. We have to square Q. So Q squared is 876,096. And then we have to divide by T. And so when we divide by T, we get 109,512. Okay. And this is one isoquant out of infinite many. In the graph, it's one of these 5, right? It's one of these 5. Okay. We have infinite many because we can draw one here. We can draw one here. We can draw infinite many isoquants between these two, infinite many between these two. So there's infinite many of these isoquants, but we've only drawn 5 of them, right? All right, so we're going to use the information above. I'm going to delete this line, and I'm going to delete this Q here. I'm going to type L equal to 88.5 because that's the first labor quantity in our table. And then I also type K equals 177 there, right? Now I need the cost equation. The cost equation is the W times L, the wage times labor, plus the price of capital times capital. And then I need the production function, Q, equal to the square root of T times K times L. Okay. So when labor's 88 point, given these values up here, When labor is 88.5 and capital is 177, as it is in row 1, the cost is $3,292.20. So $3,292.20, right? And the output is 350 units, right, of product. Now, notice when I hit enter after typing 354 there. So this right here, this dashed line below this dot, that is labor at 88.5 hours. And the dashed line to the left of the dot, that's the capital level of 177. So if we expect to sell 354 units of output, cost is minimized at this dot. So if we expect to sell 354 units, we can minimize our cost by hiring 88.5 units of labor and 177 units of capital. And we will minimize our cost at that point. Okay. All right. So let's find out what happens when we increase labor to 161.25 and capital to 322.5. Okay, that cost is $5,998.50, right? And the output is 645. Okay, so when I enter the output here at 645, we see a new dot here, right? So this isoquant curve, this L-shaped isoquant curve, anywhere on it, we're producing 645 units of output, right? And this is the isocost line that represents minimum cost for the capital labor ratio of 161.25 hours of labor and 322.5 units of capital, right? So now it's increased labor to 234 units, capital to 468 units, and we get a cost of $8,704.80. And the output is 936. All right. So we have output of 936. Now on this isoquant curve, anywhere along this, right, as our capital labor ratio changes along this middle isoquant curve, we're able to produce 936 units. This downward sloping line that is tangent to it at this dot is the isocost line that represents minimum cost for output of 936. And that occurs when labor is 234 units and capital is 613.5 units. Right. Now let's change labor to 306, 306.75 units, and capital at 613.5 units. When we have this capital labor ratio, we can produce 1,227 units of output at a cost of $11,411.10. Now we're on this fourth isoquant curve. Along this fourth isoquant curve, output is 1,227, right? This isocost line that is tangent to this isoquant curve at this point represents the cost minimizing level of capital and labor. that is sufficient to make 1,227 units of output. And that labor level is 306.75 units of labor and 613.5 units of capital, right? And then finally, we have this 379.5 units of labor and 759 units of capital. And those two combined can result in output equaling 1,518 at a cost of $14,117.40. And this capital labor results in an output of 1,518 units. So anywhere on this isoquant curve, the firm is producing 1,518 units. This line that is tangent to it at this dot represents the minimum cost to produce 1,518 units, right? And that minimum cost occurs when labor is 379.5 units and capital 759 units, okay? Now, it was assumed above that the firm expects to sell how many units of product? It was given to us that the firm expects to sell 936 units. Now, that is in my table, it's the third row, right? It's the third row here. So we expect to sell 936 units, right? So 936 units of product is what we produce anywhere on this blue isoquant. Anywhere on this blue isoquant, the firm is producing 936 units of output. At this level, its costs are minimized when it demands how many hours of labor. So I'm in the third row. You might be in a different row. I'm in the third row, and the firm wants to hire 234 hours of labor, right? And when I hit enter, the isocost line that represents the minimum cost to the firm of producing 936 units, right, is highlighted right there, right? Now, at the intersection or the tangency point of this isocost line and the isoquant curve, labor is 234, right? 234, and capital is 468, right? So now we can erase all of the other isoquants and erase all of the other isocost lines, right? And we have our original optimal solution here, right? With labor being 234 hours and capital being 468 units, right? Now, the marginal rate of technical substitution, hang on. I got to fix this. I inserted this word technical. So the marginal rate of technical substitution, this is analogous to the marginal rate of substitution in utility theory. The marginal rate of technical substitution equals what? Well, on the isoquant, the slope changes as we move down along the isoquant. Here, the slope is close to zero. Here, the slope is really, really large, right? So the slope is changing as we move down along the isoquant. At point zero, though, the marginal rate of technical substitution, the slope of the indifference curve, if you look really closely, right near this blue dot, the slope of the isoquant equals the slope of the isocost. And it only happens at one point at this blue point. At any other point along the blue curve, this is not true. But at this point, the slope of the isoquant equals the slope of the isocost. And if you remember, the slope of the isocost was 2, right? And 2 is the ratio of the wage rate divided by the price, the hourly price of capital, right? The per hour cost of capital. You divide this by that. And it happens to be 2 here, right? So at this point, and only at this point, the marginal rate of technical substitution equals a -2 here, right? And this implies that the firm will substitute 2 units of capital for 1 hour of labor I inserted this ceteris paribus statement, right? Okay, so the marginal rate of technical substitution equals a -2, which implies at the optimal solution, at this blue dot, and only at this blue dot, the firm will substitute 2 units of capital for 1 hour of labor, holding output constant at 936 units, and technology constant 8%. Remember, our production function, right? Our isoquant assumes quantity is 936 and technology is 8, right? So we got to hold those two constant. We're holding those two constant along this blue curve, right? So I had to make sure that was emphasized. And I put that text in italics, right? Now, if the firm sells its product at $9.30 per unit, right, its hourly revenue is going to be equal to what? Let me reset the labor to 234 here, right? Labor is actually 234. We're in the third row of our table. Capital is equal to 468. Our costs are $8,704.80 per hour. We're producing 936 units per hour, right? If our price is $9.30, then our revenue is going to be P times Q, right? So Desmos is going to multiply this 930 times this 936, right? And hourly revenue is $8,704.80 per hour. Economic profit is the revenue minus the cost, right? So we're going to subtract the cost here. And our economic profit is 0. And this is true in the long run. Why is 0 economic profit long run true in a perfectly competitive market? Well, if this firm were making a profit in the short run, an economic profit in the short run, and it was a substantial economic profit, maybe the owner of the company drives around in a customized Lamborghini, sending everybody a signal that, hey, the market I am selling product in, it is very lucrative. And those signals are received by entrepreneurs. Entrepreneurs seeing this guy drive around in a Lamborghini goes, hey, wait a minute. He's got above normal margins in that market. I'm going to go out and get a loan. I'm going to arrange some capital. I'm going to jump in this market. And when those firms jump in that market, the price is pushed down through competition. And the prices will be pushed down and the quantities will rise until the last firm enters and those economic profits go to 0, right? So that's why in the long run, economic profits are 0, because any economic profit greater than 0 is going to invite competitors, right? That's why it's really important. If you start a business, it's really important to don't show off, right? Don't send entrepreneurs signals that your line of work, your market in this market in this niche that you've created by selling a product, don't sell entrepreneurs, don't send them signals that the margins are above normal, right? You want to kind of Warren Buffett it, drive around an old pickup truck, live in a $300,000 house, right? Don't be seen on your home in the Cayman Islands, right? Don't post things on social media, right? The last thing you want to do is invite competition. Keep it on the down low. Keep it in the hush hush, right? All right, now, so although the cost of 379.5 hours of labor and 177 units of capital is $8,704.80 per hour, right? Let's see, 379.5 hours. Let's replace L with that. And let's replace capital with 177 and find out what the cost is. It looks like at this amount of labor demanded and about this amount of capital demanded, the cost is in fact $8,704.80. The firm's not going to choose this capital labor ratio because its output is what? Its output is only 733, right? 733. How many decimal places do we need? We need 2 decimal places. So the output, this capital labor ratio can only produce 733.06 units of output. Right? It's not, you're not able to produce the 936 that you expect to sell, right? So this would represent a bunch of lost sales, right? If you only produce 733.06 units, you could have sold 936. So this represents a bunch of lost sales. And on our indifference curve up here in our graph, this is the situation, right? When labor is 379.5, right? And capital is 177. We're on, that point is on the ISO cost line, but notice it's associated with lower output. And this output is 733.06. We could have sold 936. So being on this lower isoquant represents, if we're on this lower isoquant, we're losing out on possible sales, right? Our sales could have been much higher, right? So we're not going to choose that capital labor ratio, right? We're not going to choose it, right? If the firm hires that amount of labor and it had acquired 759 units of capital, right? The cost is in fact $14,117.4. It's this last row of the table, right? It's that last row. And the firm will produce up here 1,518 in units, right? And that puts them right here, right? It puts them on a new ISO cost line and an isoquant that corresponds to 1,518 units. This ISO cost corresponds to a cost of $14,117.40, right? Now, if the firm could sell 1,518 units, this capital labor ratio, 379.5 hours and 759 units of capital, would minimize the cost of producing 1,518 units. But the most we can sell here, the most we expect to sell is 936. So we would be what? Our output here would be way above what we expect to sell, right? Our output would be 1,518, but we only expect to sell 936. right? So we'd have excess of inventory of 582. And what do you do with excess of inventory? Well, you got to discount it, right? You got to discount it. You got to, the way you get rid of it is you got to lower the price by running a sale, right? And firms really don't like sales, right? They don't like discounting the product. Okay, so they're not going to do this point here, right? Because they're not going to be able to sell. They don't expect to sell 1,518. They only expect to sell 936, right? 936 is the quantity that is associated with this blue curve. So that's the most they can sell, right? And they don't want to have excessive inventory. So they're not going to do the gray point here, right? Now, suppose market analysts convince the firm that its sales will increase to 1,518, right? An hour in the next 5 years. Holding all of the factors constant, its alloy cost in 5 years will be minimized if it hires 379.5 hours, right? And acquires 759 units of capital, right? So now it's being told that, oh, yes, you'll be able to sell 1,518 units, right? So the firm's going to go ahead and they're going to go ahead and hire that much labor and acquire that much capital, right? That many units of capital. Okay. So the firm is going to ramp up. It will now be able to ramp up its production to 1,518. So it's going to produce 1,518, and that's going to be equal to what it expects to sell in 5 years, right? So it's going to try to match its production to its sales forecast, right? So now it's got a new isoquant, this red one. That gray isoquant became a red one, right? So this is its new isoquant at 1,518 units of production, right? And that's going to cost them. We already calculated this. $14,000. $14,117.40. That's how much they're going to cost to produce those, right? Okay, when we hit submit here, that changes. Oh, sorry. When we hit submit here, that changed the color of this isoquant to red. Hitting submit here changed the color of the isocost red. And all of these dashed lines and these numbers, right? So what's going on here is if all of a sudden our expectations of future sales increases from 936, the blue line, the blue curve, and it increases, and we increase our expected sales to 1,518, right? We're going to match our firm production to our sales expectation. We're going to minimize cost, and that means our final optimal solution will be this red dot. And so our original optimal solution is the blue dot. Our cost minimizing final optimal solution is this red dot, right? Its hourly revenue did what? We're holding the price constant, right? Let's see. We have labor at 379.5, capital at 759. The cost is $14,117.40. Output's 1518. We're holding the price constant, right? We're holding the price constant. The revenue, the revenue is $14,111 or $14,117.40, right? So the hourly revenue is $14,117.40, right? When I subtract off the cost, my economic profit is zero, right? Now, just because the economic profit is zero doesn't mean the owners of the company aren't making a return. They're making a normal return. A normal return would be, say, 5%, right? So what a normal return is you're an entrepreneur and you have two choices. You can start a firm, right? You can start a company, or maybe you just put the money in a safe investment that makes 5% a year, right? Like a government treasury. Right now, government treasuries, depending on the maturity, are anywhere from 4 to 5%, right? So you could put your money into a treasury and earn 5% a year, or you could put your money into a business. So you're earning probably a normal return of 5%. Anything above that is above normal, right? Anything above the 5% normal profit, accounting profit, anything above that is called economic profit, right? So economic profit is in excess of a normal return of, say, 5%, right? So the owners of the companies are getting a return. They're also getting their salaries, right? So all this means is there are no above normal economic profits. Okay, that's all this economic profit of zero means, right? Now, the firm's labor demand was 234, right? The firm's labor demand was 234. The quantity of labor it demanded was 234. Now, its quantity of labor demanded is 379.5. So quantity of labor demanded increased by 145.5 hours. Whoa. Whoops. I put it in the wrong spot. Dang it. Ignore this. Sorry about that. So labor demand increased by 145.5 hours, right? Now, we can graph the labor demand equation, right? I'm going to put this on pause for a second. Okay, what I did is I just assumed the slope of this labor demand equation was -5, right? I just assumed that was -5. Okay. So here's a labor demand equation, the blue downward sloping line. Now I can verify that this could be a valid labor demand equation by substituting in the original quantity of labor demanded, 234. When I plug in 234, I get a wage of 9.3. My original wage was 9.3, right? So maybe this is accurate, right? We don't know what the slope is. Assuming the slope is correct, this is the labor demand equation, because when we plug in the 234 that we demanded initially, right? When we plug in the 234 initially, we get a wage of 9.3, right? Okay, assuming the slope of the labor demand equation is still -5, right? This equation in line 3 of Desmos is the new labor demand equation, right? Because when quantity of labor demanded is 379.5, L1 here, this value is plugged into here, right? And we get a wage of 9.3. when the labor demanded by the firm is 234, L0 plugged into here gives you 9.3. So if the -5 is, accurate, this is the firm's labor demand curve before the output, before firm sales were expected to increase to 1,518. And this is labor demand after its expected sales were to increase to 1,518, right? So this is the before. This is when output is expected to be 936, and this is when output is expected to be 1,518, right? And the wage is 9.3 because the wage was held constant, right? So if I unassign L's that right there, and I unassign this one, I can see that my labor demand must have shifted from where it was initially to out here, right? Why did labor demand increase from blue to black? Well, it makes sense, right? It makes sense that it shifted from blue to black because we were expecting to sell only 936. Now we expect to sell 1515. So when your firm expects to sell more product, you're going to get a parallel shift of your labor demand equation. Okay. And ignore this. That was a copy and paste mistake right there.